Hello, everyone. Welcome again to the One World Combinatorics on Words seminar. I'm pleased to have Florin Manea speak to us today from the University of Göttingen. And he's going to speak to us about linear time subsequence and supersequence regex matching.
Yeah, I hope everybody can hear me. Hi, I'm Florin, and I see a lot of people that I know in the audience. So hello to all of you, and I'm sorry that I didn't meet you in the last, I don't know, couple of months or so. Um, so it's a pleasure to be here. Thanks a lot to the organizers for inviting me, and to Narad for the introduction. Today I will give a talk about a paper that was published at MFCS 2025 this summer. And it's work done together with Antoana Marilli and Tina Ringleb and Markus Schmidt. And basically, maybe it's worth saying this project started as a discussion in a Dutch seminar on regular expressions. So today I'm going to talk about some, let's say, very easy to state problems. And hopefully, we were surprised to find solutions for these problems that are so efficient, and we will discuss a bit about this. And it's all related to regex matching, where regex matching means that you are given a regex, you are given a word, and you want to decide whether the word is in the language described by this regular expression. So this is a very basic problem, which is very well understood. What we did here was to consider this problem in a kind of a more relaxed setting. So, oops, sorry. This is the outline of my talk. So I will start with some preliminaries to give you some idea what's going on in case, basically to set all the definitions so that we talk the same language, more or less. And then I will discuss several variants of the problems that we have approached in this paper and give you also like kind of an overview about all the problems that were discussed in the paper. So basically a regular expression over some alphabet sigma. So with sigma, capital sigma, I denote the alphabet that we are working on is defined recursively. The empty set is a regular expression which describes the empty language. And then every letter of the alphabet, including also the empty word, is a regular expression, which describes the language which contains a single word, namely the word X, where X is, as I said, either a letter of sigma or the empty word. And then we have the recursive definition. Basically, if S and T are two regular expressions, then their concatenation, S dot T, is a regular expression, S or T is a regular expression, and S star is a regular expression, where the language described by the concatenation S dot T is the concatenation of the languages of S and T. And then the regular expression described by this OR operator, so S or T is the union of the two languages described by S and T respectively, and S star describes the clinic closure of the language described by S. And for instance, if we take here an example, if we take this regular expression A concatenated with B star or B concatenated with A star, describes the first half, describes the language AB to power K, or K greater than 0. And the second part describes the language BA to power K for K greater than 0. And of course, due to this disjunction operation, we take their union. And it is well known that the regular expressions describe exactly the class of regular languages. And there is also, so another way to describe this class is, of course, by considering that the regular languages are exactly those languages accepted by NFAs. And in this particular case, we will consider epsilon NFAs. These are NFAs which also have epsilon transitions, so transitions labeled with the empty word. In general, an NFA is five tuple where we have a finite finite set of states Q. In this talk, we will assume that the size of Q is always n. So when I use this letter, I mean the number of states in my automaton. We have an initial state Q0 and final state QF. So for the sake of this talk, so during this talk, I will assume that there is a single initial state and a single final state. This is easy to achieve when we work with automata NFAs with epsilon transitions. And then we have a set of transitions, sorry, delta, which can be seen as a function that maps a state and a symbol or the empty word to a state. So basically, this being a non-deterministic automaton, we will have for a single state, so for some input state and input symbol, we will have multiple states as targets. The size of the automaton is basically the number of transitions that this automaton has. This NFA is essentially a graph with labeled edges. So we will look at the size of this automaton as the number of edges in this graph. So, of course, when we look at this interpretation, of course, the directed edges labeled by symbols from sigma are given by the transitions. And in general, a run of A on a word W is a path that starts from the initial state and leads to some state P, which is labeled by W. Of course, we read the labels of the edges along such a path, and well, you ignore the epsilon labels in the sense that you just concatenate these labels. So the concatenation with the empty word doesn't change at all the word. And a run is called accepting if the end state of the run, this P, is the final state. And basically, the language accepted by A is the set of labels for accepting runs of the automaton on. Yeah, so it's the set of labels for accepting runs of the automaton. So W is accepted if there is an accepting run of A on this word W. There is a classical construction that connects regular expressions and epsilon NFAs. This is the Thompson's construction. And this shows that a regular expression can be converted in linear time into an epsilon NFA, such that the language accepted by the automaton is exactly the language described by the expression. And moreover, this automaton has size linear in the length of the expression. So when I say the length of the expression, you just count the symbols that you need to write this expression. And this is relatively easy. If you have a union, you just have to do, create an automaton for each element of the union. For the star operator, you need to do a cycle labeled with epsilon. And for the concatenation, it's really easy. You just concatenate the two automata that are labeled with that are obtained for the sub-expressions. And I mean, if you want it to be extremely precise here, you could have, instead of this Q2, probably it would have been easier to have. So in the most classical way, you could have had an epsilon transition, but in this case, as we have a single final state and a single initial state, you can omit this epsilon transition. Anyway, the idea is that we don't need to actually go deeper into this construction at all. The idea is that basically, if you have a regular expression, you can get in linear time an epsilon NFA which accepts the language described by this regular expression. So this allows us to replace regular expressions by epsilon NFAs in the rest of the talk. Another thing that comes into play when we talk about, for this paper and this presentation is the notion of string relation. We will consider here several string relations. In general, a relation is defined in the most classical way. So it's a subset of sigma star times sigma star. So basically it's a set of pairs of words. And we define this set lambda indexed by the relation for a word W as the set of words U, which are in this relation smaller or equal, let's say, with W. So the set of all strings that are in the respective relation to W. Of course, this notion can be this notation and notion can be lifted to languages, and we can define lambda for L as the union of lambda for the respective relation for all the words of L. For instance, relations that are considered in this paper are the prefix relation. So this smaller or equal 3 gives us all the prefixes of a word W. So U is in this relation if U is a prefix of W. Infixes or factors, subsequences and supersequences. These are important for our talk here. We say that U is in the relation sub with W if U can be obtained from W by removing some of the letters of W. So U is a subsequence of W. There are many names for these subsequences, scattered factors or subwords. I prefer subsequences. It seems to me, well, I mean, I prefer it because it's the name that you use for this in classical literature on string algorithms. I think this is the best explanation why I take this name. So supersequence, U is a supersequence of W if W is a subsequence of U. I think that you might be in a bit, so this notation might look a bit misleading. So, this is why we use this index here, sup. So otherwise you might be tempted to think that U is smaller or equal to W in some sense, but this means that this U is a supersequence of W. Also, sorry, we talk about left extensions and extensions. U is a left extension of W if U is obtained from W by putting something in front of W, and U is an extension of W if W is an infix of U. So if prefix and infix are connected to left extensions and extensions respectively, and subsequences and supersequences are connected between them. Okay, so these are the definitions. Basically, what are the problems that we look at? The basic problem from which we start, which is very well understood, is deciding whether a word is in the language described by a regular expression, which has its counterpart for NFAs. You are given a word and you want to see if this word is in the language accepted by epsilon NFA. And we will look at matching problems for a relation. So for a given relation, the respective matching problem is to decide whether there exists a word which is in the respective relation to the input word W, which is also in the language accepted by an automaton A. You can also think about this in terms of regexes. As I said, it's the same thing due to the Thompson's construction. Then you have the mean and max variance, where you look for let's say for the mean variant, because this is what we will see more often. You will look for the shortest word, which is in the respective relation to W, and also in the language accepted by A. And of course, I mean, not of course, but last is the universal variant, where you want to see if all words which are in the respective relation to W are in the language accepted by A. So let's take this relation to be the subsequence relation. Basically, in the first question, we look whether there exists a subsequence of W which is in the language accepted by A. Then in the second problem, we look for the shortest, respectively longest subsequence of W, which is in the language accepted by A. And in the universal variant, we look whether all subsequences of W are in the language accepted by A. And what we have tried to do, we have tried to understand as precise as possible the complexity of these problems for the six relations that we have mentioned before. So here we have the results. The first table, we have the upper bound, so basically the algorithmic results. And in the second table, we have the lower bounds for these problems. Most of the time, these are conditional, where these are lower bounds which hold under the strong exponential time hypothesis. In particular, saying that there is no algorithm that runs faster than 2 to n for a satisfiability problem with n variables. Just to give like a very short description. So what are the algorithmic results? Basically, for most of the standard, or let's say not standard, but the relations which are related, which are defined based on factors, infix, prefix, extension, and left extension. The matching problem as well as the mean and max problem can be solved in quadratic time, or maybe it's better to say rectangular time. So it's the product between the length of the word and the size of the automaton. And all these bounds are optimal in the sense that a faster algorithm or polynomially faster algorithm would contradict the strong exponential time hypothesis. These optimality results come from also the algorithms are quite straightforward. So basically all these nine results here, so the let's say upper left corner of this table come from the standard matching algorithm for NFAs, while the lower bound come from an orthogonal vectors reduction from the orthogonal vectors problem, which was showed by I think Abud and Indik in one of the first papers related to conditional lower bounds for string problems. Then, if you look at the universal problem, it's quite interesting. We also have optimal results. Again, for the prefix case, it follows in the same way as the others. For the infix case, we have a slightly more complex algorithm which runs in the length, so n squared times m, and there you cannot improve this polynomial. So polynomially, so basically you cannot decrease these two by any epsilon, no matter what kind of dependency you allow on the size of the automaton. Again, this is an orthogonal vectors-based lower bound. For extension and left extension, this universal problem. So are all words that are found in a respective relation with a given word, are all of them part of a regular language given by a sigma, by an epsilon NFA. This is p-space and also p-space hard. So for the subsequence problem and the supersequence problem, I think that the most surprising results are the matching results. So surprisingly, and I think this was really unexpected when we started talking about this problem, deciding whether there is a subsequence of a word which is accepted by an automaton, respectively deciding whether there is a supersequence of a word which is accepted by a given automaton, can be done in linear time. So we have optimal results for these two problems. If you look at the mean and max problem, you get quadratic algorithms again, which are optimal. Interestingly, the max sub and mean sub problems, so longest subsequence, which is in a regular language. This is kind of a longest common subsequence problem, by the way. And the shortest supersequence problem, where you measure the supersequence between the word and the automaton, they can be solved in quadratic algorithms. We will discuss immediately how. I mean, not immediately, maybe in 20 minutes. And for those, you have OV lower bounds. So these are conditional lower bounds for any type of algorithm. For the shortest subsequence and longest supersequence problem accepted by an automaton, we have kind of weaker lower bounds. Basically, we show that there is no combinatorial algorithm that runs faster than these complexities by a polynomial factor. Now, what does combinatorial algorithm mean? That's a bit of a good question because there is no standard definition for that. But in general, the idea is that you can say that an algorithm is combinatorial if there are no hidden calls to fast matrix multiplication subroutines. So basically, this combinatorial algorithm should be read in a sense, an algorithm where we do not hide any kind of complicated algebraic approaches, like, for instance, Strassen's algorithm. This is not a combinatorial algorithm, right? Or these new fast matrix multiplication algorithms, they are not combinatorial algorithms. Combinatorial means, in a sense, that we look at the combinatorial structures that occur in the problem rather than using some sort of algebraic properties of the input that we have. So as for instance, there are these fast matrix multiplications that use properties of the ring over which the matrices are in order to get this type of algorithms. So, I mean, now, of course, if I'm allowed to make this parenthesis at this point, I think this is a question of taste in the end. If you want to believe that this type of lower bounds are very meaningful in terms of the complexity, I think that they are more meaningful in terms of establishing an interesting connection between problems, like in our case, triangle detection in graphs, as I will show later, and some string problems like these min sub or max sub problems. But we will talk more about it when the time comes. Now, I'm going to focus in this talk, in the rest of this talk, on these columns. So basically, what's done here in blue, I will tell you how these problems are solved for subsequences, and then I will also show you the intuition behind these lower bounds. So you can see, by the way, there are also some non-conditional lower bounds like this Cohen P hardness and this P space hardness here. So these are not conditional on any type of hypothesis like the orthogonal vectors conjecture or something like that. So getting now to the results, the basic techniques that one needs to understand for these problems, it's also the basic technique behind the regex matching problems. You are given a word, an epsilon NFA, and you want to decide whether this word is in the language accepted by the automaton in quadratic time. And this is done by something which is called, as the title says, state set simulation. Basically, you maintain the set of all states P. So at step I, let's say, you maintain the set of all states P such that there is a word, there is a path, sorry, labeled with the prefix of length E of the word from the initial state to these states P. So this is also called the state of active states at step I. And, basically a state is active at step I if it is in this set Si. So if it's reachable by a path labeled with the prefix of length I starting in the initial state. Of course, a word is accepted by the language if and only if doing this state set simulation, so computing all these sets, you get that the final state is active at the end of the simulation, so basically at step length of W. In general, how do you update? Well, that's relatively easy. You first do the closure of so when you move from set Si minus 1 to set Si, you take all the states which are reachable by one transition labeled with letter Wi from the states in Si minus 1. And then you do the epsilon closure of these states. So basically, once you computed this, you had the initial state, then you made a transition with letter Wi, and then from this state, you take everything that is reachable by epsilon transitions. So not only in one step, but also in multiple steps. So for instance, if you want to look here, let's take the word W, which is ABBA, and this is my automaton. And basically, as at the initial step, you have S prime 0. So basically, you look at the states which are reachable from Q0 with the empty word. Initially, of course, only Q0 is reachable, but then we have to take its epsilon closure. So also Q1 is reachable. Then in the next step, you look at the states which are reachable from these hashed states with the letter A. And basically, you get first Q1 and Q2 due to this transition. So we had this transition from Q0 with A that led to Q2. And then you had this transition that's looped in Q1. And these are the, let's say, basic states in S1. And then if you you have to take their epsilon closure. And in this case, nothing changes because there are no epsilon transitions leaving from these states. So there are no other states which are reachable by empty words. Now, if you take the second letter, B, you have to see what states are reachable from the hashed states with the B. First, you get Q2 and Q3 due to the highlighted transitions, and now you take the epsilon closures, And you see, you would get Q4 in one step, but you also get Q6 because it's reachable by two epsilon transitions from Q3. So you can continue this process and basically get, obtain these states as one, as two, as three, and so on, as four. So at the end, we see that this is let's say, final set that is reached in this simulation. So basically, this is S4. These are the states which are reachable after reading the entire word. And the final state, QF, is not one of them, meaning that this word is not accepted by the language. So it's not part of the language described by this automaton. It's not accepted by the automaton. Let's now focus on the sub-matching problem. So basically, you are given a word W and an epsilon NFA A of size M. The word has size N. Then the sub-matching problem, so basically deciding whether W has a subsequence which is accepted by A, can be solved in linear time. The, let's say, standard trick would be to transform A into an epsilon NFA, which accepts the upwards closure of A. So basically accepts all the words that have, so these are all the words for which there exists some word of the language accepted by A, which is a subsequence of this initial word. So all the words U for which there is a subsequence which is in A, in the L of A. And basically we just have to check whether W is accepted by this automaton. This, this transformation from A to A sub, it's actually very easy. You just have to add some dummy transitions that preserve the state but are labeled with all letters of the alphabet. Intuitively, when reading W, this would allow us to ignore some letters of W and just concentrate on the subsequences of W and accept W if there is a path from the initial state to the final state. So the non-ignoring transitions of an accepting run of W on A sub essentially spell out the subsequence of W accepted by A. And the main observation comes, let's say, well, maybe this is not really a very, let's say, deep but interesting observation, which would lead to a nice algorithm. This comes from a paper by Bachmeier, Luttenberger, and Schlund from, let's say, 10 years ago. We see that when a state appears in the set of active states in a simulation of a sub on some word, then this one would stay active until the end of the state set simulation. So basically, you can just loop in that cycle whatever you read in this state, whatever you read, and this one stays active. So basically, this state set simulation yields some increasing sequence of sets of states. And therefore, there are at most n+1 different sets of active states. So once something became active, it stays active. So these sets can only increase, with every letter that we read. Now, if you would like to do state set simulation on this automaton, this becomes too slow. Because you always look at this state and you always simulate these closures, and basically this would lead to a ultimately quadratic algorithm, exactly like in the case of the regular regex matching. Now, however, due to this property that we have seen, we realized that basically it's enough to only run this state set simulation on the automaton A while reading W, while only considering the new active states at each step. So basically, once we read some states, and we read the new letter, basically we just explore the new states that are added through in the previous step. So what we are going to do, we are going to compute, if we have Si-1, we are going to compute its closure when reading letter I in the following way. If P is in this state and state Q is added to some transition, then Q will become part of the simulated states for all j greater than I. And this also tells us that the transition that we have just used to add this Q we can be ignored from that on. So it's enough to keep kind of a list of the unmarked transitions sorted by the source state, and then use these transitions when we reach this state the first time. So sorted by the source state and the letter that we want to use. So somehow the idea is that you have your state that you set of states that you maintain, and when you read a new letter, you basically explore all the you explore the transitions leaving this state which are marked with that letter, and those transitions will never be considered again because they have given us everything that they could give us. And computing the epsilon closure can be done exactly the same. So basically, is that once you reach the state, its state's reached, you don't have to look at it ever again. It will not tell you anything new. And yeah, basically, this can be implemented by storing the transitions in a clever way. I mean, maybe it's not even that clever. You just have to store the unmarked transitions sorted by the letter that labels them. And yeah, basically, this when you so basically in this list, H of A, so H indexed by a letter, there are just the available transitions which were not used before. And when computing the next step, you use all the transitions which are labeled with the available transitions from your current state, and you then remove them once they have been marked. So with a bit of care, everything works out fine, can be organized well. So the update step can be done by just using the transitions, marking and removing them, storing all the new reached states, then computing their epsilon closure. What we then need to do is to put on the transitions that have now become available in the lists nicely sorted. And for the complexity of this algorithm, it is important to note that every transitions either is not marked at all, or it becomes marked in the computation of some epsilon closure and then ignored, or put in some of these lists at some update step, then marked at some later update step, and then ignored. So basically, if you amortize this, so if you do this computation by, let's say, amortized analysis, you will see that the complexity of this algorithm, which is just state set simulation, is linear in the size of the automaton because every transition is used once or marked once, deleted once. And of course, you just read the word only once. So submatching can be done in linear time plus, so linear time both in the word and the automaton. Now let's move on. So for super matching problem, the trick is pretty similar. So you can get, sorry, I'm just going to quickly go back here. You can get a similar theorem. And the trick is that in that case, you can compute a similar automaton which accepts the downward closure of A. And then this, when you do state set simulation, the set of the sets, so the sequence of sets is then decreasing, not increasing. So again, it has some good property which allows you to implement this state set simulation, let's say in a kind of an easy way. That particular algorithm is a bit more difficult because, yeah, so it needs some pre-processing before everything runs smoothly, but the complexity is still linear. You can have a look at these algorithms in our paper, which is both on archive and also in the proceedings of the MFCS conference. Well, the part in the proceeding misses some details, so I would recommend the archive version. Okay, so we were here. We wanted to consider the mean and max variant of the matching problem. So basically here you are given a word W and an NFA, and you want to find, let's say, the shortest subsequence of W, which is accepted by this NFA. And for short, the scheme is the following. You build a product graph between the automaton and the word, and this will have size quadratic. And you also put weights on the edges of this graph, which are 0 and 1, uh, depending on whether the respective edge is, in a sense, should be considered when we compute the shortest, respectively longest subsequence, supersequence of W, which is accepted by A. We will give the details in a second. The idea is that this graph is a DAG, and it has easy to work with edges, so the weights are nice, and then you can compute in such a word the shortest, respectively longest word U of which is a subsequence of W, uh, which is also accepted by A, as it corresponds to a minimum, respectively maximum weight between the source and the sink of this product graph. And moreover, this can be done in linear time using some, breadth first search, for instance. So the trick is that this graph is simple. So let's first see how you construct this graph. Essentially, you will do a product so the vertices are essentially pairs of positions of the word and state. The source is 0q0, and the sink is length of WQF. And in general, you have a transition which has no label. So the transitions are also sorry. If you have a transitions, I'm sorry. If you have a transition in the automaton, which is an epsilon transition, then you add an edge from IP to IQ. So the transition was from state P to state Q. Then you will have a transition between these two nodes, which has label epsilon as well and has weight 0. If you have a transition with a letter from P to Q, and this letter is the ith letter of the word W, so our input here, then you add an edge from level I minus 1 of this graph to level I from state P to state Q, and this transition is labeled with A and has weight 1. So this means you take letter WI, kind of consume it when you move along this edge. And moreover, what you will add is essentially, because, due to the nature of the problem, so we look at the subsequence matching problem, you still have to be able to ignore letters of W, just like we had before. If you look at position I of W and state Q, you can advance, skip over letter I of W by moving from level I minus 1 of this graph to level I and preserving the state. This time you will have label epsilon and weight 0. And sorry, basically just to what we wanted here, we wanted to find the shortest path, let's say, in this graph that connects the source to the sink. This basically means that you have to advance and have a minimum cost. So basically, this selects the minimum amount of letters that would take us of W that take us from the initial state to the final state in the automaton due to this product construction. Now, because this graph is a DAG, so you see you never have. So if you look at this value here, the first element of the pair as the level of the node, I already used this kind of intuition in my explanation. Basically, you always advance down this graph. You never go back. So this is a DAG. Your edges have nice weights, so basically you can compute shortest path, longest path with respect, or let's say path of minimum weight, path of maximum weight, and so on, just by doing breadth first search, for instance, or depth first. And the idea is that, or dynamic programming in the end on this product graph. And yeah, you get this type of quadratic algorithm, which is relatively simple. This type of product graph, it's a very standard construction. So especially in this area where you want to simulate the action of an automaton on a word. So this is a simple algorithm. The question is whether you can do better than that. And The answer, especially, I mean, it's especially interesting in the case of the mean variant of the submatching problem. We have proven that this can be solved if this problem can be solved in less than quadratic time, where less means polynomially less. So we do not exclude, algorithms that run in nm divided by some log polylog factor or something like that. We exclude algorithms that run in so in nm to power 1 minus epsilon. And if you would have such an algorithm, then we could decide whether a given dense graph with n nodes has a triangle. So this means, exactly you have like an edge from node I to node J, and an edge from J to K, and an edge from K to I in this graph. This has a triangle, so you would be able to decide this in less than cubic time. And any truly subcubic in the number of nodes, of course, n is the number of nodes of this graph, any truly subcubic combinatorial algorithm for triangle detection would give us a truly subcubic combinatorial algorithm for Boolean matrix multiplication, which is considered unlikely. So once again, this just excludes combinatorial algorithms for these problems. It doesn't tell us much about general algorithms. We will make also a comment on that, so in a second. Yeah, so um, basically, how do we obtain this lower bound? We have to take an input problem of the graph problem, an input of the graph problem. So you have a dense graph and you want to decide whether it has triangles. We will convert it first into an NFA. This basically has some states Pi, Qi, Ri, and Si indexed um, by some number by this I, which is between 1 and n, and it has a source S, a target T. Actually, it has some more states, but these are the important states in this automaton. And we should think as this Pi as some entry point, the ith entry point, Si is the exit point, and Qi and Ri are some exit points. So this is basically the structure of this graph. Here you have the Pi's, here you have the Qis, here you have Ri's and Si's. And then there are some dummy states that connect the state S to these Pi's, and some dummy states that connect S1, Si, Sn to T. So this is called the left part, this is the middle part, and this is the right part. The trick is that these states are not too many here in this area. We will see immediately. So the trick now is that let's focus on the middle part because this is the important one. You have an edge from Pi to Qi labeled by epsilon if there is an edge in the graph connecting I and J, vertex I and vertex J. Same here from Qj to Rk if there is an edge from vertex J to vertex K, and here if there is an edge from K to I. Intuitively, if there is a triangle in the graph, then there is a path that goes from Pi to Si. And this also goes the other way around. So G has a triangle containing Vi, if and only if there is an epsilon labeled path from the ith entry point to the ith exit point. Now, it's also important what we put in front and in the back. In the front, we will put a length 2n plus 1 minus I path from S to Pi, where the last I edges, the edges closest to the middle part, basically the ones that end in Pi, are labeled with A, and the prefix is labeled with P's. So this is, you will need some states to model this, but you can do it with a linear number of states because somehow you can, start here with a path and then just deviate from this path as you go deeper on this level. So I'm not insisting on that. You just have to believe that this kind of tree has a linear number of nodes. Same here. You will connect Si to T by paths that have the form A star B star. This time they have length n plus 1 plus I, and the first n minus I edges closest to the middle part are again A's, and the rest are B's that go to the end. And now we see that every string accepted by MG must go through exactly one entry point and exit. So basically it goes here somewhere, then goes here and then exits. And so therefore it has the form B star, A star, B star. And an accepted string going through the ith entry and jth exit point has length, what's written here, 3 times n plus 1 plus j minus I, and has exactly n minus j minus I occurrences of A. So basically you have to add the a's that are here in the end with the a's that are here in the beginning. And this is, I rewrote what we had on the previous slide. Now, if you consider the string W, which has the form b to power 2n, a to n, b to 2n plus 1, and the query is the minimal length of or basically the question, the input is given, like you are given that automaton, this W, and we want to check if the minimal length of a subsequence of W accepted by MG is equal to exactly 3n plus 1, then this is a lower bound on the length of the accepted subsequences, because if you take a subsequence of W and this is accepted by the ith entry and jth exit point, then you has at most n occurrences of A, and basically you get that the length of U will be 3n plus 1 plus j minus 1, which is greater than this capital N if j is greater than I. So lengthened subsequence of W can only be accepted using the same entry and exit point I, which is possible only if G has a triangle. So sorry, I'm rushing this a bit because I would like to cover everything that I have. Essentially, the only thing that we need to note here is that basically the product of W and the size of the graph is cubic, because this graph is quadratic due to the thing in the middle. The graph was dense, therefore the automaton is dense. And if we can solve this mean variant in a time which is n times the size of the automaton to 1 minus epsilon, then we could also decide whether the graph G has a triangle in truly subcubic time. So this proves a lower bound. Essentially, that simple algorithm that we had based on the graph product is optimal. The max variant of the submatching problem is also lower bounded, but this time everything follows in a more direct way from the longest common subsequence problem. As I said, this can be seen as the longest common subsequence problem between a word and an automaton. Yeah, exactly. You just have to build, let's say, the downward closure of U, and then you essentially just run. So when you want to include when you want to encode the longest common subsequence in problem into this max variant problem. So essentially, this covers everything that we had about subsequence. Subsequences, basically, we had the matching problem, the mean and max matching problems. All of them are solved optimally by, let's say, kind of natural algorithms. The only thing that remains is the universal submatching problem, where you are given a string and an automaton, and you want to see whether all the subsequences of the string are accepted by the automaton. And what we could prove is that this is CoMP complete. For the membership in CoMP, you just guess a subsequence and you check it. This can be done obviously in polynomial time, actually in linear time. For the hardness, that's an easy yet nice solution or reduction. You consider a 3CNF formula over n variables, so a set formula, and then you build an NFA which accepts all strings of length k between 0 and 2n except n. So k, this length, is anything between 0 and 2n except n. And also all the strings of length n that represent non-satisfying assignments of f. And basically, I mean, this is not hard to build this epsilon NFA. And now what you can see is that if you intersect the language accepted by this NFA with the language of all the words of length n, which can be described as the subsequences of this 0, 1 to power n. This is a so-called n-universal word, so a word that has all subsequences of length n as so all words of length n as subsequences. So if you check if this word, take this word instead of w and this NFA instead of the one given here, then basically the problem here will give you the answer yes. So all these subsequences are accepted by the automaton if and only if f is not satisfiable. So basically, this is a way to decide whether a certain 3CNF formula is not satisfiable. Therefore, the lower bound, the NP hardness. And basically, this concludes my talk. I will stop on this slide where you have the overview of the result. Once again, what we have concentrated on, it's this column that refers to subsequences. All the others are covered in our paper. Thank you.
Great. Thank you very much, Florin. Does anyone have any questions? Yeah, Hajime.
Thank you for nice talk. I'm sorry if I'm if I misunderstood, but you considered subword for it. So the relations in means subword. Is it right?
I don't understand. Can you?
So in the first line, so in the first column, in means you in W
Yeah,
means you in
it's
subword.
substring. Yes. So basically, it's a factor of the.
So that means you occurs in V. So my interest is in variant of such cases. For example, U occurs K times in V. So is
Oh,
it possible?
yeah, that's a good question. I don't know. I mean, so basically, you want you want to parameterize this relation by just looking at the factors of W which occur at least k times in the words, and you want to see if one of these is part of a regular language. So I think that basically, so I didn't think of this one. That's basically the first answer. I think that the problem is a bit more difficult because you would need to move away from any type of state set simulation because you have to include some sort of counting in your like I don't know simulation of the NFA on top of this word. So yeah, I to be honest, I don't know. I mean, it seems that maybe it's a bit more complicated. I think that, probably you can still do it in polynomial time, but I guess that this doesn't tell you anything, and it's also like a trivial observation. And in terms of lower bounds, I have no idea. But it's a good question, so I think it's worth looking at.
Thank you.
Yeah, sorry for not being able to say anything more. I
Ah,
didn't think
ah,
about this. It's a nice
ah,
question.
Thank you.
Are there any other questions? Sung Min.
Hi, can you hear me?
Hi, Sunmin.
Hello. So I have one question. So what happens if the given automaton is a DFA, not an epsilon NFA? Does the hardness result inherit from the results, or is it somehow is does it somehow make the problem easier?
So first of all, it makes in general, if you are only to look at the matching problem, the problem becomes much easier because you lose all the dependencies on the automaton, right? You don't have to do state set simulation. You just, move along the graph as the letters tell you. So I think that the problems become easier. I don't know about the mean. So probably if you look only at subsequences and this LCS problem, this stays as hard as the one for NFAs, because basically you can compute this automaton. This subsequence automaton can be constructed as a DFA in linear time. So basically, if we are going to talk, sorry, I have to move the slides and I moved my cursor. So here, not here. This one here, so this AU sub can be constructed as a DFA. So this lower bound will be preserved. So I guess that some of the lower bounds that, upper bounds and lower bounds that we have here, so this one, for instance, and probably also this one, so the one that are conditioned by the orthogonal vectors conjecture stay the same. I don't know about the combinatorial lower bounds, so we didn't really look into that. I think it's also something natural to look into. But yeah, maybe it still stays quadratic. So I guess that, I mean, this is I guess maybe slightly educated, so it's not, I wouldn't yet put money on that, but I guess that everything that is here quadratic stays quadratic, and everything that is where you have here these lower bounds, probably they also kind of stay the same. I guess here the situation changes a bit because you look at contiguous parts of the word and then you just simulate a DFA on them. What I can tell you, there are some, so with one of my PhD students, we also proved some lower bounds for some problems related to DFA's recognition. So basically, you want to see if there is a word accepted by a DFA which has a given word as a suffix or something like that. I think this can be also proven to be, quadratically hard. Well, I don't know how they connect to this. So it's, again, a good question. I didn't really look into the details. I think that it's something that one could look into, but it might be that the results are not so interesting.
I see. Thank you for the answer.
Yeah, thanks. And yeah, sorry again for not being able to say, hey, you should do that, this and that.
It's okay.
Yeah, anyway, nice to see you, Sungbin.
Yeah, nice to see you too.
I have a similar question. Are these problems all undecidable for context-free languages?
I would guess so. I mean, checking if something is a subsequence. So it probably relates very well to the checking the emptiness of a context-free language. But this is, yeah. So definitely undecidable. No, wait. So I don't think that they are undecidable for context-free languages. I think that they are undecidable for context-sensitive languages. For context-free languages, I think that uh, you can build the downward closure, or at least you can build some. I mean, you don't necessarily have to build the automaton for the downward closure, but probably you can construct a context-free grammar that accepts the downward closure of, quite easily and efficiently, and then you can just run some algorithm to see, for instance, if a subsequence of a word is. I mean, wait. It's my answer is a sequence of weights. So basically, they are decidable. So let's say that this subsequence matching, it just means that you have to check if there is a subsequence of W which is generated by a context-free grammar. You just can try all the subsequences, right? This shows an easy decidability.
Okay, right. Okay.
Yeah, and I guess that you can do it more efficiently than that by just being clever on how you check this. So you can build in, for instance, the CYK algorithm. You can just omit some letters when you build the dynamic programming matrix. And so I think that everything stays decidable for context free. I wouldn't be able to tell you the exact complexity. We looked at, so we have some papers where we look at the languages of so the sets of subsequences of the languages described by context free grammars. So this is a paper that we had last year at the Isaac conference. So some of the results probably follow from that one. I don't know about these min and max problems. I think that these are interesting. So again, decidable, but I don't know how to do them efficiently, I guess. But yeah, so as soon as you move further away from context free, the problem becomes undecidable due to this, is there a subsequence of W accepted by this language means that you have to have something accepted by the language. So in a sense, you check emptiness. So if emptiness is undecidable, then you get problems. Otherwise, I think, yeah, you have to look with, let's say, more fine-grained methods.
Okay, great. Thank you. Are there any other questions? All right. If not, thanks again, Florin.
Thank you for the invitation and for the nice questions.